Hi everyone, my name is Eric Mottler, and for my Mechanical Engineering 5332 course project, I am presenting on the role of X-ray and CT technologies in the advancement of 3D printing. First, let's get into some background on 3D printing. It's a groundbreaking tool that's being used in the manufacturing industry now, and it gives companies a way to prototype their products before they bring them to market and use methods such as injection molding and machining. So it's a cheaper, faster, and more efficient way to get their ideas into a physical implementation so they can test them before they go to those more advanced, time-consuming, and expensive methods. 3D printing is also known as additive manufacturing, and parts are not only used for prototypes, they're also used for direct-to-consumer applications, which we'll learn more about a little later. So there are three main types of additive manufacturing. The first being FDM, or fused deposition modeling. This is when a solid filament is extruded through a heated nozzle. These filaments come in large spools and are purchased relatively cheaply. The layers come out thicker and are visible to the eye, but there's not a lot of work that has to be done after the part is printed. These are some of the most common in the consumer area, not used as much in industry, because it's a really cheap way to get into 3D printing. SLA, or stereolithography, is another type of 3D printing. It uses a liquid vat of material and a laser that's directed through the vat and hardens the polymer layer by layer. This allows for an extreme amount of detail to a point where the layers are sometimes not even noticeable by the human eye. It's hard to tell if these parts are even 3D printed based on FDM. They look like they're almost injection molded. They're a little stronger than FDM because it has better layer adhesion compared to that other type, and it's more common in rapid prototyping for industry. And SLS, selective laser sintering, is when a laser is shined in a pattern into a powdered material, and these are mostly metals used in industrial applications, and these parts are extremely strong, and again, the layers are not visible. The surface finish of these parts is not as smooth as SLA, but it's like a nice powdered and a uniform roughness on the outside, where again it doesn't seem like it's 3D printed in the traditional sense, like in FDM. And it's important to note that SLS is what is most often examined by X-ray technologies, because this is what is used in industry. Some issues that X-ray technologies can help to solve in the additive manufacturing field are unwanted porosity, surface roughness and imperfections, and deformation caused by residual stress. Porosity is just how it sounds. The surface finish of the products can have a varied appearance and a varied feel, and this is not good for taking these products to market or using them as prototypes. We want the model that engineers are using to be exactly preserved when it comes out of the 3D printer, but if the printer is introducing this porosity, it's unwelcomed. That goes along with surface roughness and imperfections too. Deformation caused by residual stress is, as the printer is moving layer by layer, it heats where it is fusing the material to the solid object, and that heating, cooling at every layer causes residual stress to occur. And this deforms the final part so that it no longer matches the dimensions that were modeled on the computer. And to solve this problem, engineers and scientists have turned to XCT, or X-ray microcomputed tomography. This is a quantitative analytical technique, and it's mainly used for the porosity qualification in additive manufacturing. It also helps us to find keyhole pores, which occur when a laser in SLA and SLS printing is shined into the material to fuse the material to the solid. Gases escape from the melted plastic or metal, and those gases penetrate into the solid because they're superheated and cause a void in that plastic or that metal. And then when that void collapses and the gases evacuate, the metal or the plastic holds that shape, leaving to a porous surface all along the outside of the part. Diving deeper into the keyhole pores issue, Carnegie Mellon recently did a study using an ultra-high-speed synchrotron. Looking at the diagram below, which shows their test setup, you can see that the undulator houses the element that creates the X-ray beam, and the slits and shuttles form that beam into exactly what the researchers want to exactly concentrate it on their samples. And a laser scanner takes the X-ray signal before it passes through the sample. That beam is reflected through the mirror and then through the lens, and then it passes through the sample. After that, the detector is able to read the data that's coming from the X-ray beam based on what's passing through and compare that to what the laser scanner is seeing to create our data for this experiment. In this diagram below, you can see the different stages of the pore formation. You can see that in slide A here, the melt pool occurs. That's when the melting material happens. Then the vapor from that material starts expanding into our base model right here in slides B through F. And that once that vapor collapses and is extracted out of the model, that pore is left in its place, weakening the model and leading to a poor surface finish. Residual stress is another problem that plagues the additive manufacturing field. The repetitive heating and cooling of the model as it's being printed leads to this residual stress, which leads to part failure down the line once the model is created. Residual stress is unwanted in the case of 3D printing in most applications, but it can actually be used, like in the case of turbine blades, where a peening process shoots microparticles at the blades to impart stresses on that material and actually make the blade stronger. But in the case of 3D printing, this stress is not designed, and we want to take it out of the process. And taking residual stresses and understanding what causes them and how we can limit them makes additive manufacturing better. X-ray technologies help us to understand this residual stress. CT, or industrial computed tomography, is really important in this field. It helps us take an extremely detailed pictures and different slices of these finished parts to see what's going on inside of them as well as on the outside. And it helps us validate the dimensions we're seeing to make sure that what we have printed in the printer matches what we modeled on the computer. The data obtained from the CT scans improves the additive manufacturing process because it shows us at what parts of our machine tool operation the residual stress occurred. And the CT process is also used a lot in the biomedical field, which we'll cover soon. The biomedical field integrates CT scans and additive manufacturing technology in one of the biggest ways. It was first used by N.J. Mankovic in 1990. He used CT scanners to create 3D models of patients' internal bone structures. Then he used SLA printing to create anatomical models that exactly match that human structure. He used a GE 8800 at 120 kilovolts and 120 milliamp seconds with 1.5 millimeter slice thickness at a 2.0 millimeter slice interval. This allowed doctors to test treatments before surgery. Specifically in this case, a 20-year-old with a facial deformation was scanned prior to surgery so that a doctor could prototype an implant to fix his facial deformity. A CT scan works by shooting an X-ray beam through a subject and detecting it on the other side at different orientations. So the way this machine works is it rotates around the specimen, and by shooting the beam through at different orientations, it can start to make out the shape, and more importantly, it can get different slices and cross-sections of that sample. That's what makes it so useful in imaging extremely complex parts in industry and the human structure, which is also extremely complex. XCT, or CT scanning, is also used in the biomedical field to make hip implants, which is a really common procedure that happens in the United States. X-rays are directed through the patient to make a 3D model, and intensity along a series of linear paths is measured. Decrease in intensity is characterized by Beer's law, which compares intensity reduction as a function of energy, path length, and material linear attenuation coefficient. Now, once this model is created of a person's femur, a implant can be customized so that it does not load the femur in a harmful way. Right now, implants are pretty standardized and they don't tailor to different morphology. So the wrong type of implant could cause fractures in the femur later in life. By taking this 3D model and then printing it, usually out of a titanium alloy, and customizing this print to the individual, it allows for a safer implant with less fractures down the road. And this would not be possible without the CT technology, which allows doctors to get that perfect image of the human. X-ray based technologies are extremely useful in the advancement of the additive manufacturing field. Not only do they help the printing processes get better, but they expand the implementations of the printers. So not only are the printers used in industry now in combination with CT scans, they can be used in the biomedical field to create implants and to create models of the body. These two have a really tight relationship, and together, X-ray and additive manufacturing technologies are growing together. Thanks for listening to my presentation. Here are some works that I referenced while making it.